Everybody, we are looking at natural deduction today, the proofs aspect. So we've been going over this for a little while now, the idea of converting certain propositions in symbolic form in order to seem a bit different in case we need to break them down a little further or deduce certain elements from certain pieces of more complex propositions. And today we're just going to look at that whole process and really setting up the proofs. And so when we're looking at proofs, we're essentially trying to determine the validity of an argument based on a more complex construction, a more informal construction. Truth tables are something that are helpful and good, but require a formal formulation of the premises and the conclusion. Most of the time when we're communicating, when we're writing and or speaking, you'll notice that our arguments seem to jump certain steps. We assume certain propositions or premises that are obvious. We make leaps from certain things to other things. And this won't necessarily show up in a truth table. We would need to formulate a truth table very formally, making sure that we hit every single premise and every single point, making each little connection from one thing to the next. But with proofs, we're able to use some of those laws, laws of implication, laws of replacement, in order to make jumps from one premise to the next, which will lead us to a conclusion. And so proofs are going to be a good way of determining the validity for more kind of informal formulations of arguments. So here is one example of that. Art is expensive and art is beautiful. If art is expensive, then it is coveted, and art is beautiful and coveted. And so you'll notice that the conclusion here is a combination of the two premises. However, it's making a leap to combine elements from the first proposition and elements from the second proposition in a way that if we were to create a truth table, we would need to insert an extra premise there to really highlight the fact that art is beautiful and art is coveted to get us to that ultimate conclusion. And so we want to be able to do this in a more convenient way, which is why we went through those different laws of implication and laws of replacement, so that we can see where premises or see where propositions come from other propositions and how we can deduce certain information from very complex propositions. And so this is an example of that proof. And the way we lay out the proofs is essentially starting the first lines with the premises. The last line is going to be the conclusion. And on the right column, you'll notice that the first two words, assumption and assumption, those are just going to be the premises. We're going to take those for granted. And then from those two premises, we will deduce little bits of information, always acknowledging what lines we've deduced them from and what rule we are using to deduce that information, which I'll give an example of a little bit later. But if we're looking at premise one and premise two, art is expensive and beautiful. If art is expensive, then it is coveted. We can't just assume that art is beautiful and it is coveted. We need to get there by deducing little elements of information from each of those two premises. The first is that we need to deduce that art is expensive. So if we're looking at premise one here, we see that art is expensive and art is beautiful. So from one, we can get to line 3. If we get line 3, we can use lines 2 and 3 together to get us to line 4. If we use line 5 from line 1, if we use line 1, we can also get line 5. And now we can combine elements of this proof in order to get us to art is beautiful and it is coveted using lines 4 and 5. And so I'll explain that again in a little bit using the actual names of rules moving forward. Here's an example of the same exact thing, but just using the variables instead of the particular words. And so this is how our proof is going to look. The only difference really when we're conducting a proof is that you'll see the conclusion up in line 2. and you'll see that, and it'll be signified with a slash and then the conclusion. So you'll have premise, premise, and then over on the side of the last premise, you will have a slash and the conclusion. And you won't ever have to write the words assumption. Those are just part of the premises that we take for granted. The proof actually starts when we start taking little bits of information and writing the rules of replacement or implication or different things that we can use to deduce naturally the conclusion that we're trying to get. And so when we're constructing proofs, we're always making sure that we're explaining how we get little bits of information. So for instance, if we have P and Q, we can take out P and we can take out Q individually and put them on their own line. So we know that if P and Q are true, then P by itself must be true, Q by itself must be true. And there is a rule for how we get that information. It is a simplification, and we are able to write that rule based on the first line P and Q and get P and get Q from there. Again, there will be an example here in a little bit. So this is going to be the example of how a proof is going to get set up. When we're looking at these proofs, you'll notice the premises in blue on lines 1 and 2, and then slash the conclusion. So we need to get from those two premises in blue to the conclusion. And so in order to do that, we need to break these two premises down and then recombine them in a different way in order to get that B and C. So if we're looking at this first premise, E and B, we can take out E using simplification. So if we look at line 1, using simplification, we can get E. From there, we can deduce that if E is true, C must be true. So we know that if in line 2, we have if E, then C, and we know in line 3 that E is true, then using modus ponens, we can combine lines 2 and lines 3 in order to affirm the truth of C by itself. So now we have E, we have C, and then in line 5, we are going to get B by itself using simplification again with line 1. Remember, if E and B are true, then E by itself is true and B by itself is true. So now if you look at lines 3, 4, and 5, we have assumed that E is true, C is true, and B is true. And then combining lines 4 and 5, we can then express our conclusion that B and C. And we do that through a 4 and 5 with the rule conjecture. Now, it's important to note that there are also some other ways in which we can determine the validity of arguments in these proofs. And one way of doing that is through conditional proofs. And so if this is our problem, if we're looking at if A, then B and C as premise 1, and if B or D, then E in premise 2, how can we get to if A, then E? I know that this is going to work just based on my knowledge of chain arguments, assuming that these two things are true. But how is it that I know that this works in a chain argument? Well, the reason is because I can naturally deduce if A, then E from these two premises. And so in order to construct a conditional proof, we need to basically create a proof within a proof in order to justify a conditional statement. Because remember, a conditional statement is an if-then statement. It is a hypothetical. And so we can't just go assuming that aspects of a conditional are true in case they're not, because that would be problematic. That would be a fallacy, something that we're going to cover later, begging the question fallacy. Instead, we need to make sure that we are able to assume the truth of the antecedent of a conditional. And in order to do that, we can go through using a conditional proof we're using the rule of conditional proof in order to show how that natural line of deduction works of using a proof within a proof to naturally derive this conditional statement. So here's an example of that. If P then R, if R then Q, therefore if P then Q. So based on these two premises, I know that my conclusion is going to be true. And how do I know that? Well, I can go through this process of assuming that P is true. Notice how line 3, 4, and 5 are offset a little bit. The reason they're offset is because I am creating this proof within a proof, this conditional proof, and assuming that what's indented with its offset is going to lead me to this conclusion. And so if it is the case that P is true, and I'm assuming that P is true, and that's where we get the ACP, right? We're assuming the conditional proof here. If P is true, then we know using lines 1 and 3 and the rule of modus ponens that R is going to be true. If R is true, then we can use the lines of 2 and 4 and modus ponens again to deduce that Q is true. So we know that if we were to assume P, then we would get Q. And we will bring this conclusion back online with the original premises because we know that assuming that P is true, it is going to have to lead to Q. So that if P then R, if R then Q, this inevitably will lead to if P then Q is true. Now notice how we haven't concluded necessarily that Q is true, and we haven't necessarily concluded that P is true. All that we've done here is made the logical deduction that if P and R is true, and if R is true and Q is true, then we must then know that if P is true, Q must be true. So we're creating that chain argument here. Our conclusion in this instance is a conditional as well. So it is also a hypothetical. We're not making a specific, direct, concrete claim here. We're essentially just saying that assuming these premises hold, then it must be the case that if P is true, then Q is also true. Now, in addition to the conditional proof, we also have a way of determining this validity using what's called an indirect proof. And an indirect proof does the same thing. It creates this proof within a proof. But in doing so, instead of deriving a conditional statement, we actually derive a contradiction. Because if a contradiction is created, then we know that whatever we assumed can't be true because we can't have a contradiction. So that if we assume something is true and it leads to a contradiction, we then know that that thing must be false. For instance, again, here we're just, what I just said, concluding the original statement is false and then showing where that contradiction lies. And then if there is a contradiction, we must then know that what we essentially began with, it'll be the opposite of that. So here's an example of that. So if A or B, then C and D. We're going to take that as a premise. We're going to take that as being true. And then if C, then not D. And we want to conclude that not A is the case. So a way to do this is if we're trying to get not A, we can then assume A and see where the natural deduction leads us. Because if assuming A is true and it leads to a contradiction, then it can't be the case that A is true, right? Because we cannot have a contradiction in logic. So let's assume that A is true, and we're assuming an indirect proof, right? So we have the AIP as the rule. Then, using line 3, we can then add in basically whatever we want. So if A is true, then we can add in B. A or B is true. Remember, you only need one of those to be true, so you can essentially add anything into that. So if we add A or B, knowing that A is at least true, then we can get through modus ponens using lines 1 and 4 to get C and D. Now, again, we don't need B to be true. It's just a disjunctive element that we can add. But creating that line 5, we know C and D through modus ponens based on that first premise and the fourth line. We can then look at simplifying line 5 and just getting C, because if C and D is true, it must be the case that C is true, and it also must be the case that D is true. So if C is true through simplification based on line 5, then we can look at line 2 and line 6. If C, then not D. We notice that C leads us to not D, so through modus ponens again on line 2 and 6, we can get line 7, which is not D. Remembering that D and C is the same as C and D, so if we look at line 5, C and D is true, the same, we can essentially just flip those over in line 5. So if C and D is true, it must be the case that D and C is true. We can simplify that. We can simplify 5 as well if we wanted to. It doesn't necessarily need to be in any particular order. But from D and C, we can simplify line 8 to get D. So now if you look at lines 7 and you look at lines 9, you see that we have not D and D. So that when we combine them together, D and not D are true. We can't have a contradiction like that. We can't have both D being true and not true. So we know that if we were to assume A, it would lead to a contradiction. And so it must be the case that not A is true. So through lines 3 through 10, that entire sub-proof, using the rule of indirect proof, we can conclude that not A is true and that it can be naturally derived from lines 1 and line 2. And so when we're proving these logical truths, we have a couple tools at our disposal. Again, we have the conditional proofs, we have indirect proofs, and we can basically establish the truth of this particular argument, the validity of this argument. And we can also do this with tautologies, so that if we're concluding an argument that has no premises, we can suggest by the fact that any argument having a tautology for its conclusion is going to be valid. So by assuming that A is true, then we can conclude that A is true if we needed to. But essentially, again, we're just using these to naturally deduce certain pieces of elements of complex propositions, combining them, eliminating aspects of them in order to get us to a conclusion, to show that our arguments are going to be valid. Again, another means of showing that arguments are going to be valid, but this time with more informal and more common types of expressions of arguments.